You can see the nearest star to our sun with nothing but your own eyes. It looks close enough to touch. It is not close enough to reach. Not in your lifetime. Not in your children's. There's a rocky planet sitting in that habitable zone, confirmed back in 2016. Everyone hears nearest and assumes someday. Nobody has checked the fine print on that promise. Voyager 1, the fastest object humanity has ever launched, moves at 38,000 miles an hour. At that speed, the trip to Proxima Centauri takes 73,000 years. To finish it in one human lifetime, a spacecraft would need to reach 5% of the speed of light. And no engine ever built has come within 1/100th of that. Tonight, we go through the machine called Daedalus, designed to burn tiny nuclear explosions behind it for 6 years straight. We go through a laser array spread across kilometers of open desert, built to push a chip-sized spacecraft to 1/5 the speed of light. We go through the ship nobody has designed yet, built to keep 3 generations of humans alive with no way to turn back. And we go through the strangest problem of all. The spacecraft fast enough to get there might not be able to stop. If this is the kind of night you return to, subscribe. It helps this quiet universe keep growing. Let's begin. Proxima Centauri does not look far. On a star chart, it sits closer to us than any other sun in the catalogue. Closer than Sirius. Closer than Vega. Closer than the thousands of stars that fill a clear night sky. Astronomers have measured its mass, clocked its rotation, and in 2016, a team working under the name Pale Red Dot caught the wobble of a planet pulling on it from close orbit, small and rocky, sitting in the zone where liquid water could survive. We know more about this star than about 99% of the ones you can actually see tonight. And still, nothing built by human hands has ever left the solar system fast enough to reach it inside a single lifetime. That is the part almost nobody sits with. Proxima Centauri is not far away. It is only far away in time. Here is the shape of the problem, laid out plainly, because it will take the rest of tonight to answer it properly. Can a chemical rocket close a gap this size? A nuclear engine, burning for years instead of minutes? A sail wide as a city, pushed by nothing but light? What happens to a body, a mind, 3 generations of both, sealed inside a hull for centuries? And can the geometry of space itself be persuaded to shrink rather than crossed? None of those 5 questions has a clean yes. That is not a spoiler. It is the reason this particular star, out of 400 billion in our galaxy, has become the one we keep measuring, keep dreaming toward, keep failing to reach. Tonight will not resolve that tension, the nearest star behaving, in every practical sense, like it is nowhere at all. We are going to sit inside it instead, because the sitting turns out to be where the real story lives. 4 light years, roughly 25 trillion miles, is the actual gap. Shrink the distance between your bed and the front door of your house down to 1 inch. And on that same scale, the edge of our solar system, the boundary Voyager 1 crossed after 35 years of continuous flight, would sit closer than the width of a human hair. Proxima Centauri would still be 4 miles away, measured from that same inch. That is not a neighbor down the street. That is someone living on the far side of a country you have never visited, called close only because their porch light is bright enough to see from a hill. The comparison sounds almost gentle, the way distance always does when it is folded down to something the mind can hold in one piece. It is not gentle when it has to be crossed by something with mass, carrying fuel, carrying weight, carrying, if we are honest about our ambitions, carrying us. So the question stops being whether Proxima Centauri is close. It is close. On any scale, a human being can normally use. The question is what it would actually cost to close a gap measured in trillions. Not to look at, but to touch. And the first honest answer to that question does not come from physics. It comes from the fuel tank. Every fact in that opening paragraph came from instruments pointed at a single faint point of light, patiently, for years. Proof that distance alone has never been the real obstacle to understanding something. Reaching it, physically, in a ship, remains an entirely separate and much harder problem. Every rocket humanity has ever launched works on the same principle. A firework does. Burn something fast, throw the exhaust one way, and let the ship go the other. It is a beautifully simple trade, and it built the entire space age. It is also the reason nothing we have built can seriously threaten the distance to Proxima Centauri. Not because the engines are weak. Chemical rockets are, gallon for gallon, some of the most violent machines humans have ever set on fire. The problem is arithmetic. The math does not bend. To reach a meaningful fraction of the speed of light, a rocket needs propellant, and propellant has mass, and that mass needs its own propellant to move, which needs its own propellant in turn, stacking exponentially until the fuel required outweighs anything that could plausibly leave the ground. This is not new information to engineers. It has a name, the rocket equation, worked out by a Russian schoolteacher named Konstantin Tsiolkovsky in 1903 and taught to nearly every aerospace engineer on the first day of class, and in more than a century nobody has found a loophole in it. Chemistry has a ceiling, and the ceiling sits at roughly 17 kilometers a second. About the speed Voyager 1 is moving right now, most of that speed borrowed from the gravity of Jupiter and Saturn rather than its own engine. Picture it in fuel, not physics. To push a probe the size of a small car to just 1% of the speed of light on chemical engines alone, the propellant would outweigh every gallon of gasoline ever refined on this planet, stacked into a single tank that would need its own engine just to lift off the ground. You would not be building a spacecraft. You would be building a fuel depot with a rounding error of payload bolted to the top. 17 kilometers a second sounds fast, until it is measured against the only distance that matters tonight. At that speed, the fastest cruising velocity of anything humanity has ever sent outward. The crossing takes 73,000 years. Something close to 2,500 human generations would be born, live, and die between launch and arrival. New Horizons, launched in 2006 and still the fastest probe ever sent directly from the ground without a planetary boost, would not meaningfully improve on that number. A faster launch barely registers against a gap this size. Not a mission, not even a multi-generational mission. A civilization would have to outlast itself by that many generations just to receive a single signal home from the far end. Chemical propulsion is not the wrong tool because it is poorly built. It is the wrong tool because it was built to escape one planet's gravity, not to cross a galaxy's distances, which leaves one very different kind of engine on the table, one that does not burn fuel in the ordinary sense at all. One built out of bombs. Every gram spared elsewhere on the vehicle buys back only a fraction of a gram of usable propellant margin, which is precisely why chemical engineers spend careers shaving weight off bolts and brackets that seem, to anyone outside the field, almost comically small to matter. None of this stands as a criticism of the engineers who actually built these rockets, working within real limits. Every one of them solved exactly the problem they were asked to solve, reliably, repeatedly, at a scale nothing before them had ever achieved. Set an ion thruster on a kitchen scale, and it would barely move the needle. The thrust it produces is often compared to the weight of a single sheet of paper resting in your palm. A force so faint that early engineers worried it wouldn't register as propulsion at all. Imagine pushing a car down a runway using nothing stronger than your own breath, repeated once every second, for years without stopping, and you start to sense the scale of what these engines are actually doing. And yet ion engines have carried spacecraft farther, on less fuel, than almost anything chemical rockets have ever managed. The trick is patience. A chemical rocket burns for minutes and coasts for years. An ion engine, used on missions like Dawn, which orbited two different bodies in the asteroid belt, the protoplanet Vesta and the dwarf planet Ceres, on roughly 400 kilograms of xenon, barely more propellant than a family car burns through in gasoline. Over a few summers, gaining a whisper of speed at a time until the whispers add up to something real. It is not brute force. It is patience turned into a design philosophy. And it works. It also is not close to enough. Even the most efficient ion engines ever flown top out, gaining a handful of kilometers per second over the course of an entire mission, an improvement measured in low single digits against the 17 kilometers a second. Chemical rockets already reach by other means. Stack every advantage an ion engine offers on top of the fastest chemical launch, and the total still lands short of anything that shortens 73,000 years into something a person could plan around. Solar sails offer a different kind of patience, riding sunlight instead of burning propellant at all. And they carry a real advantage: no fuel to run out, ever. Japan proved the concept could fly at all in 2010, when a spacecraft called Icaros unfurled a sail the size of a boxing ring and rode sunlight past Venus. The Planetary Society repeated the trick closer to home in 2019 with a sail called Lightsail 2 holding orbit around Earth on nothing but photons. Both worked exactly as designed, but sunlight thins the farther a sail drifts from its star, and past the orbit of Jupiter, the push all but disappears, leaving a sail with nothing left to catch. Both ideas share the same fingerprint. They squeeze a little more performance out of physics we already understand, using forces that were never built for a crossing this size. What the problem actually needs is not a gentler push sustained longer. It needs an entirely different kind of violence. And the first serious attempt to build one came out of a physicist's sketchpad in the late 1950s, proposing that a spacecraft ride not sunlight and not chemistry, but the same force humanity had, until then, only used to end wars. Engineers who work with ion propulsion describe the appeal in almost the opposite terms. Fusion or fission engineers use not raw power, but reliability, a thruster that can run continuously for years without the violent stresses a chemical burn puts on hardware in a matter of minutes. In 1958, a young physicist named Freeman Dyson left a stable academic career to work on a spacecraft that ran on nuclear explosions. The project was called Orion, and on paper, it solved the arithmetic that chemical rockets could never escape. Instead of burning fuel smoothly, a ship would eject small nuclear devices out the back, one after another, each detonation slamming against a massive pusher plate bolted to the hull. Shock absorbers the size of houses would soften the blow. The ship would ride the explosions the way a surfer rides a wave that keeps arriving, over and over, thousands of times in a row. It sounds unhinged. It was taken completely seriously by serious people, funded first by the Air Force and later by NASA, and in November of 1959, a small model called Hot Rod flew for real above a California test site, propelled 100 feet into the air on a stack of conventional explosive charges, timed a fraction of a second apart. No nuclear material, just proof that a pulsed explosion vehicle could fly straight, stay stable, and land itself in one piece. Picture standing at the center of that shockwave, not thrown apart by it but carried, cradled by a plate of steel built to absorb violence and redirect it into forward motion. That is the entire premise of Orion. Violence, aimed carefully enough and often enough, becomes transportation. The full-scale version never got its chance. The Partial Test Ban Treaty of 1963, signed to keep radioactive fallout out of the atmosphere, made detonating nuclear weapons anywhere near Earth's surface illegal for any purpose, spacecraft included. Funding dried up. Dyson spent decades afterward insisting the project died from politics, not physics, and the numbers back him up. A full-scale Orion craft, riding thousands of properly shaped nuclear pulses, could plausibly have reached somewhere between 3 and 10% of the speed of light. Hold that range for a moment, because it changes the whole shape of tonight's problem. At 3% of light speed, The crossing to Proxima Centauri drops from 73,000 years to roughly 140. At 10%, it falls to around 42, not a single lifetime. Not yet, but for the first time in this conversation, a number small enough to fit inside a family's memory, grandparent to grandchild, rather than disappearing into geological time. So now we have the first real piece, a design that could work, built from bombs humanity already knew how to build, killed by a treaty rather than a law of physics. What Orion could not solve was gentler than politics and harder to argue with. Nuclear fission, even done cleanly, wastes most of its energy as heat and shrapnel instead of thrust. A better bomb existed on paper. It just used a different reaction entirely. One that promised to burn cleaner, push harder, and run for years instead of minutes. Freeman Dyson later called his years on the project some of the most intellectually alive of his career. Not despite the strangeness of the premise, but because of it, a rare moment when serious physicists were given genuine permission to think at the largest possible scale. Some historians of the project argue a version of Orion could plausibly have flown by the late 1970s had the political will survived the treaty. An alternate timeline nobody will ever get to actually test. Between 1973 and 1978, a group of volunteer scientists and engineers at the British Interplanetary Society spent their evenings and weekends designing a spacecraft none of them ever truly expected to see built in their own lifetimes. The study's lead engineer, Alan Bond, later admitted the group half expected the numbers to collapse under scrutiny. They didn't. They called the design Daedalus. And unlike Orion, it never touched a nuclear weapon. It ran on fusion. The same reaction that powers every star, including the one currently keeping you alive from 93 million miles away. The design fired tiny pellets of frozen fuel, deuterium, and a rare isotope called helium-3 into a combustion chamber at a rate of nearly 250 every second, each one struck by electron beams and detonated in a controlled micro-explosion. 2 engine stages would burn for a combined 6 years, exactly the promise made earlier tonight, pushing the ship to roughly 12% of the speed of light before shutting off entirely and coasting the rest of the way in silence. 12%, a velocity chemistry could never touch, no matter how the numbers were arranged. Applied to Proxima Centauri rather than the star the original designers had in mind, that cruising speed collapses the crossing to somewhere around 36 years. Not a geological span, not even a full working career. A person who watched the launch as a young adult could plausibly still be alive. Still paying attention, decades later, when the data finally arrived home. Stay with that number, 73,000 years. The figure this episode opened with has just folded down to 36. A single human adulthood, because a physicist a century ago pointed out that fusion releases roughly 4 times more energy per unit of mass than fission ever could. The fuel is where the design quietly falls apart. Helium-3 is almost non-existent on Earth. Daedalus would need tens of thousands of tons of it, harvested from the atmosphere of Jupiter using robotic aerostats, balloon-like mining rigs, skimming the cloud tops for roughly 2 decades before the ship could even be fueled. 20 years of robotic mining, run continuously, just to fill the tanks of a ship that had not yet left the drawing board. The spacecraft itself was the easy part of the design. The fuel supply chain was, by the engineer's own admission, the harder problem, and nobody has attempted to solve it since. And even a fully fueled, fully built Daedalus would not slow down. There is no engine held in reserve for arrival, no burn planned to shed 12% of light speed back down to something survivable. The ship was designed to scream past its target in a matter of hours, camera shutters firing as fast as they could manage, and keep going, forever, into the dark on the other side. A civilization patient enough to mine Jupiter for 20 years still would not get a mission that stops. The design remains Decades later, a kind of reference point, every serious interstellar propulsion study still measures itself against. The first time anyone proved, on paper at least, that a within-lifetime crossing was not simply fantasy. In April of 2016, the physicist Stephen Hawking sat beside the billionaire Yuri Milner in New York and announced a project that sounded, at first, like a joke told at a science conference. They called it Breakthrough Starshot, and the spacecraft at its center would weigh about as much as a paperclip. Hold one in your hand for a second and feel how little that is. Camera, radio, computer, sail included, the entire mission weighs less than what you're holding. The idea skips engines entirely. A gram-scale chip, packed with a camera, a radio transmitter, and barely anything else, hangs beneath a sail only a few meters wide and thinner than a soap bubble. On the ground, a laser array spread across kilometers of open desert fires a beam carrying something close to 100 billion watts, focused on that sail for only a few minutes. In that brief window, radiation pressure alone, the same faint push sunlight gives to a solar sail, but concentrated to an almost violent intensity, would accelerate the chip to 1/5 the speed of light. No fuel, no engine, just light, aimed with extraordinary precision, doing the entire job in under 10 minutes. At 20% of light speed, the crossing to Proxima Centauri would take about 21 years. Add the 4 years it takes a radio signal to crawl back home at the speed of light, and the first images could plausibly reach Earth around 25 years after launch, inside a single career, inside a single unbroken stretch of attention. It is, by a wide margin, the fastest realistic proposal anyone has put serious engineering behind. The team behind it plans to launch not one chip but thousands, a swarm scattered across the beam, on the working assumption that stray dust grains at 1/5 of light speed will destroy most of them before arrival. Only a handful need to survive the crossing intact for the mission to count as a success. It is also the least like a mission in any traditional sense. The chip cannot slow down. It cannot orbit its target. It has perhaps a few seconds of useful data gathering time as it screams past Proxima's planets at 1/5 of light speed. And the raw beauty of the concept, unlimited fuel, no ship to feed or shield, is also its narrowest constraint. Whatever gets thrown at those speeds has to be small enough and light enough that the loss of it costs almost nothing. A grain of silicon can survive that kind of violence, or at least a fleet of them can, launched in swarms so that a few out of hundreds might actually arrive intact. A person cannot, not the body, not anything built to carry a body, not yet, and probably not for a very long time. So here is the first honest answer to tonight's question, and it splits cleanly down the middle. Under that laser, in that desert, humanity's reach and humanity's arrival stop meaning the same thing. Engineers on the project have compared the finished sail, in interviews, to a material closer to a soap film held rigid than to anything resembling fabric, a structure so delicate that ordinary handling on Earth could tear it before it ever reached a launch pad. So, is it actually possible? That was the question this episode opened with. And here, roughly a quarter of the way through, is the first honest piece of the answer. Yes, barely. In a form almost nobody pictures when they first ask the question. A sliver of silicon, weighing less than a paperclip, could plausibly reach Proxima Centauri within a single human lifetime, riding light instead of fuel. That much is no longer speculation. The physics checks out. The engineering is difficult but not impossible. And serious institutions have already spent real money proving pieces of it work. The chemical question, the nuclear question, the sail question, the first 3 doors named at the start of tonight, all open partway, further than most people watching a rocket launch on the news would ever guess. None of them open wide enough for a person to walk through. That is not a technicality. It is the entire shape of the problem restated. Nobody actually wants to send a paperclip to Proxima Centauri, somewhere underneath the engineering. The real question was always about us, about whether the distance could ever be crossed by something that carries a body, a memory, a civilization's continuity forward into a place none of us has ever stood. And that question does not get easier as the spacecraft gets smaller. It gets harder, because everything that makes a mission survivable, shielding, life support, redundancy, weighs exactly what a message-carrying chip does not have to weigh. Here is what almost nobody accounts for when they picture the crossing. It does not happen through peaceful, empty nothing. 4 light-years of interstellar space looks empty on every map ever drawn of it. And at the speeds this episode has been building toward, that emptiness stops behaving like emptiness at all. Mass is the hidden variable in all of this. A gram-scale chip struck by a stray dust grain loses a gram-scale amount of structure and keeps going. Most of the swarm sacrificed, so a handful can finish the trip. A crewed vessel struck by that same grain at that same speed transfers the same violent energy into walls built to keep a person breathing. And no thickness of shielding fixes what that trade does over a 4-year crossing. 20% of the speed of light turns a single grain of dust into a genuine threat. And a starship carrying people is not a grain of dust. It is a hull, thin walls holding pressure and warmth and breath against a vacuum that no longer just sits there quietly. Picture yourself aboard, not the chip. Every gram of shielding between your body and that dust is a gram some engineer has to find room for, fuel for, justify on a ship that already cannot carry enough fuel to slow back down. Whatever crosses this distance carrying a person will have to survive its own velocity as much as it survives the distance itself. And that problem belongs to physics most people have never had a reason to think about. Every gram of camera, radio, and computer aboard a Starshot-class chip has to justify its own existence against that same brutal constraint, which is precisely why the finished design carries almost nothing beyond the absolute minimum needed to prove it arrived at all. Every added kilogram beyond that bare minimum forces a cascade of new mass elsewhere in the design. More structure, more shielding, more of the very propellant this episode already spent an entire segment proving humanity cannot easily afford. Interstellar space is, on average, one of the emptiest places physics can describe. Roughly 1 single atom per cubic centimeter drifts between the stars, a vacuum so thin that laboratories on Earth cannot fully replicate it. For most of human history, that emptiness has meant safety. Nothing out there to hit you, and nothing for you to hit. Speed changes the arithmetic entirely. A spacecraft cruising at 20% of the speed of light does not experience that near vacuum as stillness. It experiences it as a headwind made of individual atoms, arriving at a rate and a violence that turns each one, briefly, into something closer to radiation than matter. Physicists who have modeled the effect describe it as flying directly into a beam of high-energy particles for the entire duration of the crossing. Not because interstellar space contains more material than anyone expected, but because velocity itself converts ordinary atoms into something the hull was never built to shrug off. For a crew, the danger is not just impact. It is radiation, plain and continuous. Shield designers working through the numbers estimate that months spent cruising through the interstellar medium at a meaningful fraction of light speed could expose a crew to a dose of radiation that would take an ordinary person on Earth an entire lifetime to accumulate. Delivered instead across a single year, seeping through walls built for warmth and pressure rather than a slow-motion storm of high-energy particles arriving from directly ahead. Even dust becomes dangerous at that speed. A single grain no larger than a speck of sand, struck at a meaningful fraction of light speed, carries kinetic energy closer to a small explosive than a pebble. Engineers studying the Icarus interstellar probe concept, a modern successor to Daedalus, proposed a sacrificial shield of solid beryllium, several centimeters thick, bolted to the front of the ship an entire layer of the spacecraft whose only job is to slowly erode away, atom by atom, absorbing impacts so the rest of the vehicle never has to. Stay with that for a moment. A shield designed to be worn down on purpose, its erosion measured and planned for years in advance, because the alternative is a hull with no shield at all, arriving at its destination in pieces too small to matter. None of the propulsion concepts covered so far accounted for this. Daedalus, Starshot, even Orion in its full nuclear form, were all designed around the question of how to reach high speed. Almost none of the early design work asked what high speed does to a ship once it is already moving that fast. A target now as much as a traveler, for every year of the crossing still ahead of it, and speed creates a second problem entirely. One that has nothing to do with shielding. The faster a ship moves, the stranger time itself starts to behave for everyone still aboard it, and for everyone left behind. Shielding heavy enough to stop that radiation outright would, in most serious mission designs, weigh more than the rest of the spacecraft combined. Turning the very problem speed was meant to solve into the reason speed becomes impossible to afford. Some proposed designs place the crew quarters directly behind the fuel or water supply itself, using ordinary mission mass as improvised shielding, a clever workaround that still adds significant weight to a ship already straining under every other constraint this episode has named. There is a comforting myth attached to fast spacecraft. The idea that going fast enough turns a long journey short, that a crew moving close to the speed of light would step off the ship having aged only months, while entire decades passed back home. The myth itself is not wrong. It is simply aimed at speeds nothing we have ever built comes anywhere close to reaching. Einstein's theory of special relativity does genuinely slow time for anything moving fast enough. A real, measured, thoroughly confirmed effect called time dilation. Satellites orbiting Earth right now have onboard clocks adjusted to account for it, fractions of a second at a time, because even orbital velocity bends time by a measurable amount. The effect is not folklore, it is engineering. The GPS system in your phone corrects for it every single day, and without that correction, the position it reports would drift by several miles within about 24 hours, routing a car toward a building that is not actually where the satellite thinks it is. Not because the physics is exaggerated in the popular imagination, but because the threshold where it starts to matter sits far beyond anything discussed so far tonight. At 20% of the speed of light, the fastest cruising speed this episode has offered a real design for, a crew would experience time passing only about 2% slower than everyone left on Earth. Across a 21-year crossing that shaves off roughly 5 months of subjective time. Noticeable on a flight log, invisible to the body, easy to lose entirely inside the ordinary drift of a long voyage, nothing close to the dramatic youth-preserving effect science fiction has trained most people to expect. The relationship between speed and dilation is not gentle, and it is not a straight line either. Time dilation barely registers at 20% of light speed, and then climbs almost vertically as velocity approaches the true limit, so that a ship at 90% of the speed of light experiences time passing roughly twice as slowly as Earth does, and a ship at 99% experiences it 7 times slower. 7 times. A number physics describes perfectly, and engineering has never once been asked to build toward. Every propulsion concept this episode has named so far, Orion, Daedalus, Starshot, tops out below that curve's steep part, the dramatic version of relativity, the one where a crew returns having barely aged while grandchildren grow old without them, belongs to speeds no engine humanity has ever proposed. Building can actually reach. So, time is not the shortcut it appears to be in the popular imagination. Not yet. Not at any velocity presently within reach. What remains true, and stranger, is that a ship fast enough to make the crossing worthwhile is also, by definition, fast enough that stopping becomes its own entire problem, one this episode has been circling since the very first minutes, and is finally ready to answer directly. None of this makes relativity irrelevant to the mission, only irrelevant to the timeline, a distinction easy to lose in headlines that treat any mention of Einstein as automatic proof that the trip gets meaningfully shorter for whoever is aboard. Physicists sometimes describe this gap between the fictional expectation and the real number as one of the most persistent misunderstandings in all of popular science, a genuine effect wildly overestimated at exactly the velocities anyone alive today might actually build toward. Every propulsion idea in this episode has shared the same blind spot. Orion, Daedalus, the laser-driven sail, all of them were designed to answer one question: how do you get a spacecraft up to speed? None of them, in their original design form, ever answer a second question that turns out to be just as expensive. The rocket equation that made chemical propulsion so limited earlier tonight does not forgive slowing down. It charges the same price twice. A ship that spends its fuel reaching 12% of the speed of light needs, in most designs, a second full supply of fuel to shed that speed again at the far end, and carrying twice the fuel means carrying twice the mass. Under Tsiolkovsky's equation, that does not double the difficulty. It multiplies it, because the fuel meant for slowing down also has to be accelerated the entire way there, dragged along at full speed for years before it is ever actually used. Not linear, not forgiving. This is the quiet reason Daedalus was designed as a flyby from the beginning. Never intended to stop, never intended to do anything at Barnard's star but take pictures on the way past at full speed. A magnetic field offers one strange way around the fuel problem. In 1988, the engineers Dana Andrews and Robert Zubrin proposed something called a magsail, an enormous superconducting loop, kilometers wide, generating an invisible magnetic field that pushes gently against the thin stream of charged particles a star gives off. Using it as a brake the way a parachute uses air, no propellant required, no fuel to run out partway through the crossing. The loop itself is the entire engine. And in the right conditions, arriving at another star's own stellar wind, it could shed a meaningful fraction of a ship's speed for free. The catch, as with almost everything in this episode, is patience of a different kind. Interstellar space carries far fewer charged particles than the stellar wind near a star. So a magsail breaking through the empty stretch between systems works slowly, sometimes too slowly to matter, and only becomes truly useful once the ship is already close enough to feel its destination star's own wind pushing back. The physicist Robert Forward proposed an even stranger fix for lightsail specifically. Split the sail in two near arrival, letting the outer ring catch the laser beam still arriving from Earth and bounce it back onto the inner sail, reversing its push. It works on paper, the momentum math checking out cleanly under ordinary physics. It also demands a laser array on Earth powerful enough and aimed precisely enough to keep hitting a target decades into its flight and light years from home, a level of precision nobody has ever had to hold for that long, over a target moving at a fifth of light speed, decades after the engineers who built the array have retired or died. Every deceleration scheme proposed so far trades one difficulty for another. Fuel for precision, precision for decades of advanced planning, and none of them has yet been demonstrated at anything beyond a small laboratory scale. None of these braking concepts has ever been tested beyond a small laboratory scale, which means every number in this segment carries real uncertainty, presented as the current best estimate rather than a settled engineering fact. Step back and away from engines for a moment and look only at energy, because underneath every design this episode has named sits the same invoice, and the invoice does not care which engine you use to pay it. Picture your own home's electric bill, then multiply it by every home, every factory, every city on the planet, all of it running flat out for 365 straight days. That is roughly the size of the check a single ship's engines would need to cash just to reach 1/10 of the speed of light. A realistic crewed vessel carrying shielding thick enough to survive interstellar dust. Life support for a crew, structure to hold it all together, would weigh somewhere in the range of 1,000 tons, modest by the standards of ocean vessels, enormous by the standards of anything humanity has ever launched past Earth's orbit. Accelerating 1,000 tons to just 10% of the speed of light takes, by the plain arithmetic of kinetic energy, somewhere in the neighborhood of 450 billion joules. Let that arrive slowly. The entire world, every power plant, every reactor, every dam and turbine and solar panel currently operating on Earth produces something close to 600 billion joules across an entire year. Reaching just 10% of light speed for one ship would consume a number close to an entire year of human civilization's combined energy output. And that is before accounting for the energy lost as waste heat, the energy needed to decelerate at the far end, or the energy required simply to keep a crew alive for the decades in between. No chemical reaction, no fission reaction, comes close to the energy density this bill demands without an impossible quantity of fuel attached to it. Fusion, the reaction inside Daedalus, gets closer, extracting roughly 4 times more energy per kilogram than fission does, and still falls short of what a genuinely fast, fully crewed mission would require once shielding and deceleration are added back into the ledger. There is exactly one known reaction in physics efficient enough to close that gap on paper: the total annihilation of matter and antimatter. Converting mass directly into energy at close to perfect efficiency, the same conversion Einstein described in a single short equation more than a century ago. It is also, by a wide margin, the strangest and most expensive substance humanity has ever tried to manufacture. Measured not in tons or kilograms, but in nanograms, produced one particle at a time at a cost that makes gold look like gravel by comparison. CERN, the laboratory that produces more antimatter than almost anywhere else on Earth, has managed to create and briefly hold on to only a few billionths of a gram of it since the facility opened, at a price that would make a single gram cost more than the entire global economy produces in a year. Even setting antimatter aside entirely, simply generating that much usable power in the first place, cleanly, reliably, and fast enough to load into a departing ship, remains a problem no nation on Earth has ever had to solve at this scale. Solar power alone, gathered across the entire planet's current installed capacity, would take years rather than months to accumulate a number this large, a reminder that the bottleneck here has never really been imagination. It has always been raw, physical, scale. If speed is this expensive, one idea flips the problem instead of solving it. Stop trying to arrive quickly and build something that can survive not arriving for a very long time. A generation ship. A vessel that never breaks any speed record at all, moving at a modest, unhurried fraction of light speed, but carries not a crew, rather a population, one that will live out full lives, raise children, grow old, and die peacefully aboard the ship, long before anyone alive sees Proxima Centauri appear out the window. The idea sounds almost gentle compared to the physics discussed so far tonight. It is not. A generation ship trades an engineering problem for a much harder one, keeping an entire closed ecosystem alive, unassisted, for centuries. With no supply ship ever arriving to fix what breaks, humanity has already run a smaller version of this experiment. And it did not go quietly. In 1991, 8 people sealed themselves inside Biosphere 2, a 3-acre facility in the Arizona desert, built to function as a fully closed ecological system, growing its own food, recycling its own air and water. Isolated from the outside world for 2 full years, oxygen levels fell so far, so fast, that engineers eventually had to pump outside air back in just to keep the crew from suffering altitude sickness inside their own sealed home. Ant and cockroach populations exploded uncontrollably, while intended pollinators died off. The 8-person crew split into 2 hostile factions before the experiment ended, unable to agree on how to manage what was left of their own world. Picture your own kitchen pantry and your own recycling bin, and imagine both have to function without fail for longer than your own lifetime, with nobody able to bring more of anything, ever, no matter what runs out first. That was Biosphere 2, scaled down, 2 years, 8 people, and a facility that could, in a true emergency, still be opened from the outside. A generation ship offers none of those exits. Whatever ecological balance the crew starts with has to hold for decades, sometimes proposed as centuries. Radiation shielding has to protect not just adults, but children conceived and born entirely inside the hull, and every mechanical system, every pump, every recycler has to run without a single spare part arriving from Earth, ever, for as long as the mission lasts. Engineers who have studied the concept seriously, including a 2011 design study called Project Hyperion, generally converge on the same uncomfortable number. A viable generation ship would likely need a population in the tens of thousands, not hundreds, just to maintain enough genetic diversity and enough redundant expertise to survive its own journey. Not a crew in any ordinary sense. A civilization sealed inside a hull, betting its entire future across generations on a closed system nobody on Earth has ever managed to keep running for longer than 2 years at a stretch. Every closed-loop life support system flown so far, including the ones aboard the International Space Station, still depends on regular resupply from Earth for exactly the failures Biosphere 2 exposed, a quiet admission that nobody has actually solved this problem yet anywhere, even in low orbit. Every failed closed-system experiment since Biosphere 2 has taught the same lesson in a slightly different accent. The difficulty scales with duration far faster than intuition suggests, which is precisely why a 2-year trial and a 300-year voyage are not the same problem multiplied, but an entirely different category of problem. If a population is too fragile a solution and speed is too expensive a one, a third option sits between them, familiar from nearly every piece of science fiction ever made about long voyages. Put the crew to sleep and let the years pass without anyone awake to feel them go by. Picture the version of you that steps into that sleep at launch, and the version that might, decades later, actually wake back up. Medicine has never tested whether those two versions would even be the same person, biologically, when the lights come back on. Not because nobody has looked into it seriously. NASA-funded studies through a company called SpaceWorks have spent real research budgets exploring therapeutic torpor, a carefully controlled, medically induced drop in body temperature that slows metabolism dramatically. Already used today in hospitals to protect trauma patients and cardiac arrest survivors during the most critical hours after injury. Cooling the body by just a few degrees can meaningfully reduce how much oxygen, food, and water a person needs to survive, the same principle doctors already use if you or someone you love ever needed emergency cooling after a cardiac arrest. A few degrees for a few days in a hospital bed, with doctors watching every vital sign, is a very different proposition than decades, unsupervised, on a spacecraft. Every study of induced torpor conducted so far has worked in a window measured in days, occasionally stretching toward 2 weeks under laboratory conditions built specifically to prevent complications. Nobody, anywhere, under any protocol, has ever kept a human body in that state for a full month, let alone the years or decades a real interstellar crossing would require, and the body does not simply pause when the mind goes quiet. Muscle wastes, bone density drops, radiation keeps arriving and keeps doing damage regardless of how slowly a heart is beating, because atoms colliding with a hull do not care whether the person inside is conscious. Some mammals hibernate for months at a stretch, ground squirrels and certain bats slowing their systems down to a fraction of normal function through an entire winter, and researchers studying those animals still cannot fully explain how their bodies avoid the muscle and bone loss that would cripple a human doing the same thing for even a fraction as long. So sleep, for now, remains a gap dressed up convincingly as a solution, borrowed wholesale from decades of film before a single real trial ever justified the confidence. It solves the psychological weight of a multi-decade voyage beautifully. Nobody aboard growing old or bored or desperate across the empty years, but it solves nothing about radiation, nothing about the unproven biology of staying suspended that long, and nothing about what condition a body or a mind would actually be in the exact moment someone finally tried to wake it back up, decades and a whole star system away from the nearest doctor who could help if something had gone wrong. Until an actual multi-year trial exists, every proposal built around suspended crews is, honestly, closer to an educated hope than an engineering plan, no matter how confidently it gets described in mission concept papers. A generation ship does not just have to keep human bodies alive, it has to keep an entire purpose alive, passed down through people who never personally chose the mission at all, who were simply born into the middle of it. Try to name your own great-great-grandparents' single deepest wish for your life. Something specific. Something they would have wanted you to still be carrying forward. Most people cannot. And on solid ground, that gap in memory costs almost nothing. Aboard a ship where the entire mission depends on that same memory surviving intact, generation after generation, it costs everything. Consider what that actually requires. The first generation launches by choice, trained, prepared, fully aware of what 4 light years and 300 years of confinement mean. Their grandchildren do not get a choice. They are born inside a hull, taught a destination they will never personally choose to travel toward, raised entirely on stories of a planet none of them has ever touched and a star none of them has ever stood beneath. By the 5th or 6th generation, everyone aboard has only ever known the ship. Earth becomes a rumor. Proxima Centauri becomes a rumor. The mission itself survives only for as long as each new generation, none of whom asked to be born into it, keeps freely agreeing to believe in it. History, even on solid ground, offers a quiet warning about how well purpose survives being handed down that long, even under far gentler conditions. A message passed from person to person, generation to generation, tends to arrive altered, sometimes unrecognizable, even when everyone involved is trying their best to preserve it exactly. Now stretch that same drift across 3 centuries and a dozen generations, sealed inside a single ship with no outside culture to check the story against, no second population living a different life to notice when something has quietly changed. Population geneticists who have studied the concept converge on another uncomfortable number, separate from the ecological one. A truly viable generation ship would likely need somewhere between several hundred and a few thousand people, carefully and deliberately paired across generations, just to avoid the kind of inbreeding depression that would otherwise cripple the population within a few centuries. That is not a small detail, and it is not one solved by better engines or thicker shielding. It is a demand for permanent, generational discipline around who has children with whom, enforced not for a single lifetime but for the entire multi-century duration of the voyage by people who did not choose the rule, and never chose the ship or the distant mission that rule was built to protect. Nobody knows because nobody has ever tried it. Whether a purpose can actually survive that long without the people carrying it quietly deciding, somewhere around the 7th or 8th generation, that the star their great-great-grandparents once dreamed about is simply not worth finishing the trip for anymore. Some proposals try to hedge against this by designing rotating leadership councils and mandatory historical education programs built directly into the ship's culture, elaborate social engineering aimed at a problem no purely mechanical fix has ever been able to touch. No simulation has ever actually tested this at the true scale required, because no simulation has ever been allowed to run for 300 years, which means the entire concern remains, honestly, informed speculation rather than settled science, however carefully reasoned, A radio message, moving at the actual speed of light, takes 4 years and 3 months to cross from Proxima Centauri back to Earth under the best possible conditions. That is the flaw. The fastest any answer could ever arrive, assuming the ship is standing still at its destination and pointed exactly the right way. Picture sending a message to someone you love and waiting more than 4 years for any reply at all. Not because they are ignoring you, but because the reply itself is still crossing the room at the fastest speed anything in the universe is permitted to travel. A ship that is not standing still, one still outbound, still climbing toward a meaningful fraction of light speed, makes the problem worse in a way most people never think to ask about. Every year it travels, it gets a little farther from home, and every signal it sends has to cross a little more distance than the one before. The gap between question and answer does not stay fixed at 4 years. It grows. Slowly and permanently, for as long as the ship keeps moving outward, until a conversation with Earth stops resembling a conversation at all and starts resembling something closer to two people, leaving letters for each other at opposite ends of a very long, very patient chain of mailboxes. The delay itself is only half the difficulty. There is a subtler problem underneath the physics, one that has nothing to do with the speed of light and everything to do with the speed of human attention. Missions that take decades tend to lose the audience that funded them long before they lose their engines. Public interest, government budgets, even the specific engineers who understood the ship best. All of it drifts and turns over on a timescale far shorter than a single interstellar crossing. New Horizons took 9 years just to reach Pluto, a fraction of a single Proxima Centauri mission. And even that shorter wait saw public attention spike sharply at launch, fade for most of the middle years, and only spike again once the pictures finally started arriving. Voyager 1, still transmitting today after nearly 50 years, survives on a shoestring budget maintained by a small, aging team, several of its instruments already switched off permanently, just to keep what little power remains, lasting a few years longer. One quiet subtraction at a time, decided by engineers managing a budget that shrinks a little further with each passing year. Now multiply that by the length of a Proxima Centauri mission. Decades of outbound flight before anything meaningful can even be reported back, and ask a harder question than whether the ship can survive that long, whether the civilization that launched it will still be listening, still funding the antenna, still teaching new engineers the ship's own language, still remembering why the mission mattered in the first place. By the time the ship finally has something worth saying back, some engineers have proposed automated relay stations, unmanned outposts seeded along the way specifically to keep a signal alive, across a gap growing too wide for any single transmitter to bridge alone, though none has ever been built or tested at anything beyond a conceptual sketch. Some engineers half joke that the real audience for a mission like this is not the generation that launches it, or the generation that receives its first signal, but every generation in between, maintaining an antenna pointed at a silence they never expect to personally hear broken. You will not find this exact failure written into any mission proposal ever published, because nobody in any mission proposal ever plans for it specifically, by name, in advance. Picture a single sealed gasket, decades into the voyage, worn thin by cold and radiation, and 100,000 tiny temperature swings nobody ever measured individually. It starts to seep, barely anything. A few molecules of coolant a day, invisible to any routine inspection that isn't specifically, deliberately looking for it. The bioreactor that gasket feeds runs a few tenths of a degree warmer than its design spec. The algae inside it, engineered to scrub carbon dioxide and breathe oxygen back into the ship's air, tolerate the drift for months without anyone noticing a change. Then a second, unrelated system fails elsewhere in the ship, drawing extra power from the same grid, and the reactor's cooling loop falls further behind. The algae's growth rate slows. Oxygen output drops by a fraction nobody would notice in a single day, and then a second fraction, and then a third. An engineer catches it in a routine report 6 weeks later. The numbers are still small. The underlying trend, tracked across weeks rather than days, is not. Fixing the gasket properly means shutting down an entire deck of the bioreactor for repairs, cutting oxygen production further before it recovers, and someone on that ship, a real person with a name and a rank and a family 2 decks over, has to decide whether to ration air now, on their own terms, or risk a harder rationing later, on the ship's terms, decided by the reactor itself rather than by anyone in charge of it. Nobody aboard raises their voice. Nobody declares an emergency over the ship's intercom. The decision gets made quietly, in a meeting room 3 decks down, by people balancing a spreadsheet against the lives of everyone who will breathe whatever air is left over after the math is settled. There is no villain in this chain. No single failure anyone could have prevented with better planning. No negligence anyone could point to afterward. Nothing dramatic enough to ever make a headline back on the world you and everyone you know still calls home. Just decades of small, ordinary wear, compounding steadily in a system with nowhere to send for spare parts and no one outside the hull who could arrive in time to help, even if a message describing the problem went out across the dark today. Now multiply that single gasket by every mechanical system a real ship would need to keep running, unattended, for 3 straight centuries. This is what a generation ship actually is, underneath the architecture and the mission statements. 1,000 small, ordinary gaskets like this one, wearing down in parallel for 300 years, with a crew whose job is simply to notice the small numbers before they become the only numbers that matter. Redundancy helps, but redundancy itself has weight, and every spare part carried against a future failure is 1 more gram the ship's own fuel budget has to somehow absorb across the entire crossing. Engineers who study long-duration systems on Earth, submarines, Antarctic research stations, orbital habitats, describe exactly this same slow arithmetic of small failures compounding the closest real-world laboratories humanity currently has for a problem no one has ever actually run for 3 centuries straight. Antimatter solves the energy problem this episode raised earlier tonight almost too well. It also creates a problem unlike anything any other fuel in human history has ever actually had to deal with. It cannot touch the container built to hold it. The instant a particle of antimatter contacts ordinary matter, anything at all, a wall, a valve, a stray molecule of air, both particles vanish completely, converted entirely into a burst of pure energy. There is no slow leak to monitor. There is no partial reaction to manage. Engineers cannot simply store antimatter the way they already store hydrogen or kerosene sealed inside an ordinary metal tank, because the metal tank itself would be the very first thing it destroys. The actual solution is stranger than any tank. Suspend the antimatter in the middle of empty space, inside a cage made entirely of magnetic and electric fields, never allowing it to physically touch anything solid at all. Devices built for exactly this purpose, called penning traps, already exist at facilities like CERN, and in 2011, physicists used one to hold a handful of antihydrogen atoms suspended and intact for about 1,000 seconds, close to 17 minutes. A genuine scientific milestone at the time, and one of the longest confinements ever achieved for a substance this dangerous to let go of even briefly. 17 minutes. A spacecraft bound for Proxima Centauri would need that same trick sustained not for minutes, but for years, decades, an entire crossing's worth of storage, with the magnetic cage never once flickering, never losing power, never failing for even a fraction of a second along the way. Try holding your breath perfectly still for even a single minute and notice how much concentration that takes. Now imagine being asked to sustain something far more precise than stillness without one single lapse for 30 straight years. That last detail is the quiet horror hiding underneath the whole idea. The trap is not just storage. It is the only thing standing between an ordinary spacecraft and an uncontrolled release of the most concentrated energy source physics allows. A power failure lasting even a heartbeat would let trapped antimatter drift into contact with the container wall, and the resulting annihilation would not damage the ship. It would erase it, instantly, converting fuel and hull and crew alike into a single flash of light, with nothing left over afterward for you or anyone else to ever piece together what had actually happened. So the substance that solves the energy problem most completely is also the substance that turns a spacecraft into something closer to a bomb than a vehicle, one that has to keep its own detonation suspended continuously without a single lapse. For the entire length of a multi-decade voyage, no human engineer has ever had to sustain anything that precisely for anywhere close to that long, in orbit, in a lab, or anywhere else on Earth. Some proposals try to soften the risk by storing antimatter in small, separated batches rather than one large reserve, trading a single catastrophic failure for many smaller ones, though the underlying containment problem never actually goes away. Researchers have proposed backup containment schemes layered on top of the primary trap specifically to buy a few extra seconds of reaction time if the main field ever falters, redundancy stacked on redundancy against a failure mode with no real acceptable margin for error. In 1960, the physicist Robert Bussard proposed an idea elegant enough, on paper, to make every fuel problem this episode has raised disappear at once. Simply stop carrying fuel entirely. Build a spacecraft with an enormous electromagnetic funnel, thousands of kilometers wide, and let it continuously scoop up the loose hydrogen already drifting through interstellar space, feeding it directly into a fusion reactor as the ship flies. No tanks to fill on Earth, no antimatter to trap, and no mass penalty for carrying propellant at all, because the propellant is the galaxy itself, gathered continuously along the way. For decades, the Bussard ramjet stood as one of the most celebrated ideas in interstellar propulsion, a design that could, in theory, keep accelerating for as long as the ship simply kept flying, climbing slowly and steadily toward a real fraction of light speed, with no onboard fuel supply ever running out along the way. Then, in 1985, the engineers Robert Zubrin and Dana Andrews finally sat down and ran the actual numbers, and the elegance collapsed under its own funnel. Not a shortage of fuel, a surplus of drag. Picture trying to run forward while dragging a net wide enough to catch the wind itself behind you. The very act of catching enough air to push against also, slowing down every single step you take. Gathering hydrogen from a medium this thin means physically catching and redirecting particles that would otherwise pass by untouched. And that act of catching them, of forcing stray atoms to change direction and slow down relative to the ship, pushes back against the vessel exactly as hard as the reactor's exhaust pushes it forward. At the low speeds where a ship would most need the extra thrust, the scoop barely gathers enough hydrogen to matter. At the higher speeds where enough hydrogen finally starts flowing in, the drag from collecting it grows so large that it can cancel out most of the benefit the fusion reaction was supposed to provide. There is a second, quieter problem underneath the first. Most of the hydrogen drifting through interstellar space is ordinary hydrogen, a single proton, not the heavier isotopes. Small fusion reactors actually need to sustain a reaction at a useful rate. The Sun manages plain hydrogen fusion only because it has the crushing gravity of an entire star and billions of years of patience behind it, neither of which fits inside a spacecraft's reactor core. The idea has not been fully abandoned. Later refinements propose smaller scoops, laser-assisted variants, and hybrid designs that only ramjet through the denser patches of the galaxy. None of them have yet solved the core arithmetic Zubrin and Andrews exposed nearly 40 years ago. A scoop wide enough to gather meaningful fuel is, by the same unforgiving physics, wide enough to catch meaningful drag. An elegant idea still waiting, more than 60 years later, for a version of itself that does not silently defeat its own purpose. A handful of researchers keep the idea alive today mostly as a design constraint worth understanding rather than a mission anyone expects to fly, proof that even a beautiful idea has to survive contact with its own arithmetic. Some newer papers explore hybrid designs that only activate the scoop in denser regions of the galaxy. patches of interstellar gas thick enough to make the trade briefly favorable, though mapping those regions accurately remains its own unfinished project. Every idea this episode has explored so far has shared one assumption without ever stating it out loud: that a ship has to move through space to cross a distance. In 1994, a Mexican physicist named Miguel Alcubierre asked what happens if space itself moves instead of the ship. Einstein's equations do not forbid it. Nothing with mass, including a spacecraft, can ever travel faster than light through space. Space itself, it turns out, is under no such restriction. It stretches and contracts constantly, and always has, long before anyone built a ship to notice. Distant galaxies are already receding from us faster than light, simply because the universe between us and them keeps expanding. No law of physics violated in the process. Alcubierre's proposal borrows that same loophole for a spacecraft. Contract space in front of the ship, expand space behind it, and let the ship sit motionless inside its own private bubble, while the bubble itself carries it across the distance, arriving without the ship ever technically breaking light speed at all. A ship inside a properly constructed warp bubble is not moving relative to the space immediately around it. It is the space that moves. Nothing in relativity objects to that on paper. Everything in engineering objects to it in practice. The bubble Alcubierre described requires a ring of what physicists call exotic matter. Matter with negative energy density, a strange and unproven property that nothing anyone has ever built or mined or manufactured has demonstrated at any meaningful scale. Tiny, fleeting hints of negative energy do show up in quantum experiments, real but vanishingly small effects that have never once been captured, stored, or shaped into anything resembling a usable quantity. Alcubierre's original 1994 estimate put the energy requirement at more than the mass energy of the entire observable universe, a number so large it functioned less as an engineering target and more as a polite, mathematical way of saying no. It is not a number you or anyone else could ever hope to gather, mine, or manufacture. Not in this century, and quite possibly not in any century. Later refinements, particularly a reshaping of the bubble's geometry, proposed around 2011, brought that requirement down dramatically into a range some physicists compare to the mass of a large spacecraft rather than a galaxy. Other physicists dispute those revised numbers entirely, arguing the simplifications used to reach them do not hold up under closer scrutiny. And even the most optimistic versions on either side of that argument still depend on exotic matter. Nobody, anywhere, has ever actually produced in bulk. So the fifth and final door named at the very start of tonight, whether the geometry of space itself could simply be persuaded to shrink, remains open, technically, only on paper, propped up by mathematics that actually works, and by materials that, as far as anyone has ever managed to confirm in a laboratory, simply do not exist in any usable form. Physicists studying the concept continue publishing refinements every few years, chipping small amounts off the theoretical energy requirement, without ever closing the much larger gap between a promising equation and a single gram of usable exotic matter sitting in a lab. Set aside, for a moment, everything exotic covered so far tonight. The antimatter traps, the warp bubbles, the fusion pellets fired 250 times a second. There is a mission on the drawing board right now at NASA's Johns Hopkins Applied Physics Laboratory that plans to use almost none of it. It is called, plainly, Interstellar Probe. And unlike Voyager 1, which stumbled into interstellar space almost by accident, a decades-old planetary mission that happened to keep flying long after its original job ended, this one is being designed, from its very first sketch, to study the boundary of the solar system on purpose. Engineers working on the concept have proposed a launch as early as the 2030 seconds. Riding a powerful conventional rocket and a gravity assist from Jupiter, reaching a cruising speed somewhere around 8 astronomical units a year, close to 38 kilometers a second. not far off Voyager's own pace, but achieved deliberately. With instruments built specifically for the environment it will fly through. At that speed, over a 50-year working mission, Interstellar Probe would travel roughly 1,000 astronomical units from the Sun, deep into interstellar space, though nowhere remotely close to another star. 1,000 astronomical units sounds vast, and it is, farther than any spacecraft has ever deliberately been sent. Measured against the distance to Proxima Centauri, it is a rounding error, something under 4% of the way there, gathered painstakingly over half a century of patient, unglamorous engineering. That is precisely the point. Nobody proposing this mission believes it will reach another star. What it offers instead is data no telescope on Earth can gather. Direct measurements of the interstellar medium this entire episode has spent time worrying about. Real readings of the radiation environment, the density of drifting hydrogen, the shape of the bubble our own sun carves out of the galaxy around it, gathered firsthand rather than modelled from a distance. Every design this episode has walked through, Daedalus, Starshot, the magnetic sail, the antimatter trap, depends on assumptions about that environment that nobody has ever actually measured directly out past the heliopause, with dedicated instruments built for exactly that purpose. There is something almost humble about it. After an episode spent circling machines built from nuclear bombs and bubbles of bent space-time, Interstellar Probe will not decelerate. It will not carry a crew, or a generation, or a single, trapped particle of antimatter. It will simply keep going, slowly, patiently, for as long as its instruments keep working and its signal keeps reaching home, adding real numbers to a problem that has mostly been solved so far in equations and design studies rather than direct observation. Missions like it rarely make headlines at launch. They rarely make headlines at all. In fact, until decades later, when a probe nobody was paying close attention to anymore crosses some boundary and reminds everyone it was still out there, still working the entire time. If it launches on schedule, you could plausibly be alive to watch its first real interstellar readings arrive. An ordinary Tuesday decades from now, the kind of quiet milestone that never interrupts your day and changes permanently what humanity actually knows. Engineers working on the concept have been careful to note that even its instruments, built to survive decades of continuous operation in deep cold and radiation, represent their own unsolved engineering challenge, one this episode's earlier segments would recognize immediately. Whatever it eventually finds will not settle the question this whole episode has been asking. It will simply make the next attempt to answer it slightly less speculative than this one. Now consider the part of Breakthrough Starshot that has nothing to do with physics at all. The money and the politics standing behind it. When the project was announced in 2016, its founders committed roughly $100 million, a serious sum for a research program and a rounding error against what the finished system would actually require, less than what you might guess a single, mid-sized power plant cost to build. Estimates for the complete laser array, the ground-based infrastructure capable of producing something close to 100 billion watts in a single coordinated pulse, tend to land somewhere in the range of several billion to $10 billion. And even that figure carries real uncertainty, because nobody has ever tried to build anything quite like it before. Cost, as large as it is only the beginning of the real difficulty. A laser array powerful enough to accelerate a nanocraft to a fifth of light speed is also, by simple physical necessity, powerful enough to function as one of the most capable directed energy weapons ever constructed, 100 billion watts aimed skyward, being difficult to categorize as purely peaceful infrastructure, no matter how carefully its intended use is described. Serious discussions of the project have had to grapple openly with that dual-use reality. Treaty implications included, long before a single watt of the real array has ever been switched on. The atmosphere itself adds a further complication, one that has nothing to do with money or diplomacy. Firing a coherent beam through miles of moving air for the minutes needed to accelerate a sail properly means fighting constant atmospheric distortion the entire time, the same shimmer that makes stars twinkle scaled up into an engineering obstacle. Proposed solutions call for adaptive optic systems correcting the beam in real time, and a site chosen specifically for thin, dry, stable air, a high desert plateau rather than anywhere near a coastline or a city. None of this makes Starshot impossible. It makes it slow, in a very different way than the propulsion problems discussed earlier tonight. The physics of the lightsail itself has been tested in miniature and mostly holds up. What remains unbuilt is everything around it. The funding at the necessary scale, sustained across decades, and the international agreements needed to reassure a nervous world that a 100 billion watt laser pointed at the sky is science and not a weapon in waiting, and the multi-decade political patience required to keep a project like this funded long after the initial excitement of its announcement has faded into routine budget meetings. So the fastest realistic path to Proxima Centauri sits, right now, less blocked by physics than by something far more ordinary: the difficulty of getting enough people across enough governments and enough budget cycles to keep paying for something none of them, including you, will live to see finished. Physics rarely changes its mind. Funding committees change theirs every few years. Supporters of the project argue the same was once true of particle colliders and space telescopes, now taken for granted. Expensive, politically fragile, decades in the making, and eventually built anyway once enough people decided the answer mattered. Proxima b, the planet this episode mentioned in its very first minutes, sits in Proxima Centauri's habitable zone, close enough to its star that liquid water is not automatically ruled out. You will never see it directly, not through any telescope operating today. It has never once been directly photographed. Every fact known about it comes from the star's own faint rhythmic wobble. A shadow of a shadow, and one detail about that star complicates the hopeful picture more than almost anything else this episode has raised. Proxima Centauri is a red dwarf, smaller and dimmer than the Sun, and its habitable zone sits correspondingly close in, roughly 1/20th of the distance between Earth and the Sunday. That same proximity, the thing that makes liquid water possible at all, is also exactly where the danger lives. Red dwarfs, despite their small size, are known for producing flares far more violent relative to their light output than anything the Sun typically manages. In 2019, astronomers watched Proxima Centauri brighten by a factor of nearly 14,000 in ultraviolet light, in a burst lasting only about 10 seconds, an eruption that would scour the upper atmosphere of any nearby planet with a dose of radiation that Earth, tucked safely much farther out and orbiting a far calmer star, never once has to withstand in your entire lifetime or in any lifetime before yours. Not because Proxima b is necessarily lifeless. That conclusion does not follow either. A strong planetary magnetic field could, in principle, deflect much of that radiation, the way Earth's own field already deflects the solar wind. Active volcanism could, in principle, keep replenishing an atmosphere as fast as flares strip it away. Both are real, defensible hypotheses, published and argued over in real journals by real scientists who study exactly this question for a living. And neither one has been confirmed, because confirming either would require instruments far more sensitive than anything currently pointed at that star. Or, more directly, an actual visit. That is the quiet joke sitting underneath this entire episode. Proxima b might be the most interesting planet within any plausible reach of human technology, sitting close enough that a sail could arrive within a single generation, and it might also be the one question this particular star will never let anyone answer from a distance. The tools that could resolve it, seismometers on its surface, direct atmospheric sampling, a probe close enough to measure its magnetic field directly rather than guess at it, all require exactly the kind of mission this entire night has spent examining the impossibility of. So the planet stays a rumor with excellent credentials. Nearby, plausible, argued over, unconfirmed. We still don't know whether Proxima b is a second Earth or a scorched, airless stone dressed up in promising numbers. And tonight, that is where this particular question gets left. Open. The way it has stayed open since 2016 and will likely stay open for a long while yet. Newer space telescopes launched since the planet's discovery keep refining the picture in small increments. A slightly better estimate of flare frequency here, a slightly tighter constraint on atmospheric composition there, without yet delivering the single decisive answer anyone is actually hoping for. Ground-based observatories continue monitoring the system for new flares specifically, building a longer historical record that future missions, robotic or otherwise, will eventually depend on to judge whether any given decade is safe to approach at all. Humanity has attempted this particular kind of patience before, at a much smaller scale, and it is worth sitting with the closest example for a moment before this episode turns back to the stars. Ask yourself honestly whether you could commit to a project you would never see finished, and notice how quickly the honest answer arrives. Construction on Cologne Cathedral began in 1248. The people who laid its first stones, master masons who spent entire careers cutting stone and setting the foundation, died knowing they would never see the building finished, never stand beneath a completed spire, never watch a single service held under a roof they helped design. Work stalled for centuries at a stretch. Funding collapsed more than once. Entire generations of builders lived, worked, and died having only ever seen scaffolding, half-finished walls, and a tower that stopped rising long before it reached its intended height. The cathedral itself was not actually completed until 1880, 632 years after the first stone was set. Using the original medieval plans, lost for centuries and rediscovered, finished at last by architects and stonemasons who never met a single person from the generation that had first started the project. 632 years. Start to finish. Far longer than the entire outbound flight of nearly every generation ship design covered tonight. And the people who began it built anyway, not because they expected to see the result, but because building something worth finishing was, itself, apparently worth doing. That is not a comfortable answer to tonight's larger question, and it was never really meant to be one. The generation ship asks something structurally similar of everyone aboard it. Lay a stone, live a full life around that stone, and hand the unfinished work to children who did not ask to inherit it, trusting a chain of strangers spanning centuries to actually finish what you started. Cathedral builders had the comfort of a city around them the entire time, a public that could watch progress, a church that could redirect resources when funding ran short, an audience that made the slow effort feel, at least sometimes, seen. A generation ship offers none of that. Its only witnesses are the people already sealed inside it, and a homeworld 4 light years away that may or may not still be paying attention by the time there is anything worth reporting back. And yet the comparison holds in one important sense. Nobody who laid Cologne's foundation stones needed to see the finished cathedral for the act of building it to matter. Whether that same logic survives the loneliness of open space, sealed hulls, and 3 centuries with no skyline to remind anyone why they started, is a question this episode cannot answer either. It can only note, quietly, that humans have, at least once, proven willing to try, laying stones for a skyline none of them would ever personally stand beneath. Modern engineers studying long-duration missions have started citing Cologne explicitly in published papers, an unusual crossover between medieval architecture and orbital mechanics that exists for exactly one reason. Nobody has found a better real-world example of the specific patience this problem demands. Other long, unfinished human projects offer smaller echoes of the same pattern. Irrigation systems maintained across centuries, oral histories passed down with almost no distortion over dozens of generations, proof that the discipline required is rare but not, strictly speaking, unprecedented. Look back, for a moment, across everything this episode has covered tonight, and a pattern starts to surface that none of the individual segments named directly One worth pausing on, quietly, before this episode turns toward its final stretch and whatever answer it still owes you. Chemical rockets failed on simple arithmetic, unable to carry enough of themselves to matter. Ion engines were patient enough. In the end, their improvement barely registered against a gap this size. Orion, oddly, never really failed on physics at all. A treaty killed it, years before the engineering ever had the chance to. Daedalus solved speed cleanly and then discovered, almost as an afterthought, that it had no way left to stop. Starshot pushed that same trade even further, buying astonishing speed at the cost of ever being able to carry anything larger than a fingernail. Antimatter answered the entire energy question in one elegant equation, the cleanest solution of the entire night, and handed back, almost immediately, a storage problem stranger and more dangerous than the fuel it was meant to solve for in the first place. The Bussard ramjet, chasing endless free fuel across the galaxy, drowned in its own drag before it ever managed to get moving fast enough for the idea to matter. The generation ship, alone among all 10, gave up on speed entirely on purpose, and in exchange inherited a different, considerably harder debt. Centuries of biology, culture, and discipline, all of it required to hold without a single failure. Warp geometry solved distance itself. On paper, elegantly enough to make every other idea tonight look crude by comparison, and asked in return for a substance nobody, anywhere, has ever actually managed to hold in their hand. 10 separate attempts, 10 meaningfully different engineering philosophies, spanning bombs, sails, magnetic fields, and bent space-time itself. Notice across all 10 what none of them actually managed to solve. Not the physics of going fast, which turns out, in one form or another, to be achievable with tools already in hand or close to it. If you go back through tonight's episode looking for the one thread connecting every failed idea, this is it. What nobody has solved is the physics of enduring. Building something, a hull, a habitat, a chain of trust passed hand to hand across generations that keeps functioning correctly for decades or centuries without a single moment of outside help arriving to fix what breaks. That reframes tonight's opening question more precisely than it was first asked. Reaching Proxima Centauri was never really a question of speed. Even though speed is the number every headline reaches for first, the one this episode itself opened with, it is a question of endurance, measured not in kilometers per second but in years of unbroken function, unbroken funding, and unbroken purpose, a currency none of tonight's propulsion concepts actually trade in, no matter how fast any of them promise to fly you there. Naming the pattern does not make it easier to solve, but it does change what the next useful question actually is, shifting the conversation away from faster engines and toward the much stranger problem of institutions built to outlast their own founders. Framed that way, the question this episode opened with stops sounding like a puzzle waiting for a clever answer and starts sounding like something closer to a commitment, measured in generations rather than in cleverness. Every mission this episode has walked through, whatever else it solves or fails to solve, shares one final property almost nobody mentions out loud when the engineering gets exciting. Whoever signs off on the launch will very likely be dead long before anything real ever arrives. Not figuratively, and not as some poetic flourish about the slow passage of time. Literally, mathematically dead, given even the fastest realistic proposal this episode has taken seriously. A 25-year-old engineer who signs off on a Starshot-class mission at its optimistic best could plausibly live to see the first images return. Decades later, an old woman or an old man watching data arrive from a chip she helped design in her 20s, anyone attached to a generation ship, or to Daedalus in its full 6-year burn, is agreeing to something categorically different. To spend an entire working life on a problem whose answer belongs, by design, to people not yet born, that is worth sitting with for a moment, because it separates this project from almost every other ambitious thing humans build. A dam gets used by the people who funded it. The hospital treats patients within the lifetime of the donors who paid for it. Even Voyager 1, still calling home after nearly 50 years, was built by engineers who expected, at most, to see its planetary flybys, never imagining a shrinking team of their own successors would still be listening for its faint signal decades after most of the original team had retired or passed away. Even the largest wars and the largest migrations resolve, one way or another, inside a single human span. A mission to Proxima Centauri asks something rarer: total commitment to an outcome the committer will never personally witness. Offered freely, without the reward structure almost every other human effort quietly depends on. Proxima Centauri is not far away. It is only far away in patience, and patience is a currency every person eventually runs out of, whether or not the mission they funded ever reaches its destination. The engineers who work on Daedalus-class propulsion studies today already know this. Plainly, without needing anyone to point it out. They are not building something for themselves. They are building something for a version of humanity that gets to stand somewhere none of them ever will. Looking back at a sun that, to that future crew, will just be one more star among the thousands scattered across an unfamiliar sky. You will not see Proxima Centauri reached in your lifetime either. In all likelihood, no matter how this episode's numbers eventually shake out, neither, most likely, will your children, under most of the realistic scenarios this episode has laid out. None of that uncertainty is a reason to stop asking the question. If anything, it is the reason the question keeps getting asked at all, generation after generation, by people who somehow keep finding it worth the asking. Some mission architects have started designing for this directly, building in deliberate handoff points, ceremonies, and documentation practices meant to carry purpose across a generational gap, the way a well-run family business sometimes manages to survive its founder's retirement. Some engineers describe this openly as the most honest form of scientific optimism available to them, building carefully toward an outcome they will never personally verify, trusting the discipline of the work itself, rather than any promise of seeing it through to the end. Step all the way back out now, past the engines, past the trapped particles, past the bent geometry of empty space, to the actual point of light in the sky. This entire episode has been circling. If you are somewhere south enough to see it, Alpha Centauri is not a memory of a star. It is closer to a rumor with excellent timing. 4 years and 3 months old by the time its light finally lands on a retina, older than most of this year's headlines, older than several recent, ordinary memories, arriving tonight carrying information about a star system exactly as it looked back when the light first left it, not as it looks at this exact moment, which nobody on Earth can currently know. Most people north of the equator's midline will never see it rise at all. Alpha Centauri stays low, or vanishes entirely. The farther north a sky happens to be, one more small reminder that the universe was never arranged around anyone's convenience. That gap, 4 years and 3 months of pure travel time for something moving as fast as anything is physically allowed to move, is the smallest version of the exact problem this whole episode has been sitting inside. Even light, the fastest possible messenger the universe permits, cannot make that distance disappear. It can only compress it down into something survivable enough to actually look at. 4 years and 3 months folded into a single, steady point of white in a dark sky. This episode opened with a tension it promised not to resolve. A star close enough to see, mapped down to an individual planet, and still, in every practical sense, unreachable. Nothing covered since has actually closed that gap. Chemical rockets, nuclear pulses, laser sails, antimatter traps, generations sealed inside a hull, none of it turns 4 light years into something a single, uninterrupted human life can casually cross. The tension is still sitting exactly where it started. This episode having promised at the very beginning not to resolve it. What has changed across everything this episode has walked through is not the distance itself. It is how precisely and how honestly The actual shape of that distance can now be described. Engine by engine, decade by decade, failure by failure. Feel your own breath for a second. In and out. Ordinary, unremarkable, happening on a planet that is itself moving, steadily and continuously at over 60,000 miles an hour, around a star that is moving faster, still around the center of a galaxy that is moving faster again through space. Nobody has ever fully mapped. Distance. Out here, in whatever direction anyone chooses to look, was never really the opposite of connection. It has simply always been the space something has to cross, patiently and completely, to prove the connection was ever real in the first place. Every other star scattered across that same sky carries its own version of this same delay. Seconds for the nearest planets, millennia for the faintest visible points, a quiet reminder that no one has ever actually seen the universe as it is at this exact moment, only as it recently was. Somewhere in the middle of an episode this heavy, it is worth admitting something a little lighter. Science fiction figured out interstellar travel a very long time ago, and figured it out beautifully by simply refusing to explain how any of it actually works. Warp drive, in most versions of Star Trek, is treated as a settled piece of background technology, no more remarkable to its characters than a car engine is to a modern commuter. Nobody aboard that fictional ship spends the episode discussing exotic matter requirements or negative energy density. They just press a button. The stars stretch into a wash of light, and the crew arrives somewhere else in time for the next plot point. It is one of the most efficient storytelling devices ever invented, because it lets the story skip directly past every single problem this actual episode has spent its runtime taking seriously. The fuel, the deceleration, the radiation, the centuries of patience, none of it needs solving if the plot simply declares it solved and moves on to the next planet. Real physics is considerably less polite about it. The writers of that fictional universe borrowed Alcubierre's name for their version of the drive decades after the fact. A nice bit of trivia that runs the wrong direction. The real physicist came second, publishing his Genuine Mathematics in 1994. Years after fiction had already made the idea feel ordinary, familiar, almost boring. Alcubierre has said, more than once, that he was partly inspired by watching that same fictional ship do the impossible on screen and wondering, half seriously, whether general relativity actually forbade it. It turns out relativity does not forbid it. Engineering, materials science, and the actual physical existence of exotic matter still very much do, stubbornly, regardless of how confidently a television script glosses over the details. There is something genuinely funny buried in that gap if you let yourself sit with it for a moment, instead of rushing past. An entire branch of theoretical physics exists partly because a physicist enjoyed a television show enough to ask a serious question about a silly premise. And the honest answer turned out to be stranger than the fiction. Yes, technically, maybe, if a civilization can someday manufacture matter that behaves like nothing anyone has ever actually held. Fiction skipped the hard part by simply declining to mention it. Reality, as it almost always does, insisted on showing every last step of its work, in full, whether anyone watching particularly wanted the homework or not. There is a real comfort hiding inside that difference, oddly enough. A universe that insists on showing its work is also a universe that can, eventually, be understood, checked, and occasionally proven wrong in ways that open new doors rather than closing them. Fiction's warp drive will always work exactly as written, forever, because nobody ever has to actually build it. The real version stays truly uncertain, honestly open, which is a far more interesting place for a real civilization to stand. Other franchises solved the same narrative problem differently. Hyperspace lanes, folded space, wormholes conveniently placed near every major settlement, each one its own quiet acknowledgement that telling a good story across interstellar distances basically requires cheating somewhere. None of this research has ever actually stopped. Not once. Not even during the long decades when nobody outside a small, dedicated circle was paying any attention to it at all. It has simply stayed small, patient, and largely unfunded, carried forward year after year by a modest number of people who kept working on it anyway, for reasons that rarely made it into any funding proposal. You have almost certainly never heard of the organizations that have spent decades keeping this exact question alive between headline moments, and that is, in its own way, part of the point. The Tennessee Valley Interstellar Workshop, a gathering of scientists and engineers that started meeting regularly back in the 1990s, and Icarus Interstellar, a group formed specifically to revisit and update the old Daedalus design using decades of newer materials science, eventually merged in 2021 into a single organization called the Interstellar Research Group. It still holds annual conferences today, small rooms full of specialists, comparing notes on fusion, pellet yields, and shielding mass budgets. Sessions most of the public will never read a single headline about, let alone attend. NASA's own Innovative Advanced Concepts program funds a rotating slate of speculative propulsion studies every year, some of them directly relevant to nearly every idea this episode has walked through, most of them concluding, honestly, that more research is needed before anything resembling a real mission becomes possible. This is not the version of progress that makes for dramatic television, the kind you might expect after an episode spent talking about nuclear pulses and antimatter traps. Nobody is racing anybody toward a finish line. There is no countdown clock ticking down in mission control, and no launch dates circled on a calendar with any real confidence, let alone a press conference promising results within a tidy, reassuring decade. What exists instead is closer to a slow, unglamorous accumulation. A paper published here, a small grant awarded there, a design refinement that shaves a single percentage point off some engineer's fuel estimate, the same quiet pattern repeated across institutions and decades by people who mostly already know, going in, that they will not personally live to see the actual mission fly. That patience is, in its own quiet way, as much an answer to this episode's opening question as any single piece of propulsion physics has managed to be. Reaching Proxima Centauri does not currently require a breakthrough nobody has thought of. It requires several genuine breakthroughs stacked on top of each other, sustained funding across generations of researchers, and a civilization willing to keep asking the question long after it stops being fashionable to ask it. Every organization named in this segment is, in its own modest and mostly invisible way, already doing exactly that. One unglamorous paper, one small conference, one shaved percentage point at a time, decade after decade, without ever once needing an audience to keep going. Attendance at these small, specialized conferences has grown slowly but steadily over the past decade or so, a small, genuine sign that the question is not fading even as it remains, for now, comfortably outside the mainstream of space exploration funding. Younger researchers entering the field today often describe discovering it almost by accident, one conference paper leading to another, until a subject with almost no formal academic department anywhere still somehow gathers enough committed people to keep its research moving forward year after year. Put every idea from tonight in order, not by how exciting it sounds, but by what would actually have to happen first, in what order, and a plausible, unglamorous sequence starts to emerge, one you could, in theory, actually watch unfold across your own lifetime, piece by piece. It begins, most plausibly, with precursor missions like Interstellar Probe, gathering direct measurements of the interstellar medium this episode has spent real time worrying about, slowly replacing decades of assumption and modeled guesswork with decades of actual, measured data, gathered firsthand rather than inferred from a comfortable distance. Somewhere alongside that, in laboratories rather than launch pads, propulsion concepts get tested at a scale nobody can build a starship at yet. Small laser sail demonstrations within the solar system, miniature fusion ignition experiments. The unglamorous decade-by-decade grind of proving a principle works before anyone commits real money to building it at full size. Terrestrial fusion research matters here more than it might first appear to. In December of 2022, scientists at the National Ignition Facility achieved fusion ignition for the first time, a reaction that released more energy than the lasers put into it, a genuine milestone, decades in the making, celebrated properly around the world at the time, and still nowhere near the kind of steady, commercially usable power a real propulsion system would eventually need to draw on. Every fusion-based propulsion idea discussed tonight, Daedalus included, depends on exactly this kind of terrestrial progress maturing first. A civilization that cannot yet run fusion power plants reliably here on Earth is, quite simply, not yet a civilization ready to build a fusion-powered starship, no matter how compelling the blueprint looks on paper. Only after that groundwork is laid, plausibly, does something like the full Starshot laser array stop being a speculative sketch on a whiteboard and start becoming a realistic multi-decade infrastructure project built the way large particle colliders and space telescopes already get built today, out of necessity rather than choice. Slowly, through uneasy international cooperation, one budget cycle after another, survivable only if enough governments keep agreeing to fund a piece of it every single year. None of this collapses neatly into a single dramatic breakthrough you might read about one morning and never think about again. It stacks, one unglamorous layer at a time, the same way every large thing humans have ever actually finished building got finished, not by a single genius solving everything at once in a flash of insight, but by enough ordinary people doing enough ordinary, careful, occasionally tedious work across enough decades that something extraordinary eventually falls out the other end of the process, almost as a quiet afterthought to all that patience. None of these steps requires a law of physics nobody has discovered yet. Only sustained will, sustained funding, and enough decades of ordinary follow-through to let each stage actually finish before the next one has to begin. Skip a step in that order. Attempt the laser array before the fusion economics exist to support it. For instance, and the same project that could have succeeded patiently tends instead to collapse under its own premature ambition. A lesson space agencies have already learned the hard way more than once. Before this episode turns toward its final stretch, it is worth remembering something you already carry inside you. Whether or not you have ever thought about it in these terms, reaching an impossibly distant place with wildly inadequate tools is not actually a new kind of problem for this species. Humans have solved a smaller version of it before, more than once, without antimatter, without fusion, without a single calculation of relativistic time dilation. Polynesian wayfinders crossed thousands of miles of open Pacific Ocean over the course of centuries, settling islands so remote and so widely scattered that some of the individual voyages covered greater distances than the entire width of the continental United States. Using nothing but the stars overhead, the pattern of ocean swells felt directly through the hull of a canoe, and the flight paths of ordinary birds returning to solid land somewhere at dusk. No engines aboard those canoes, no satellite navigation, no radio, no way to call for help if a voyage went wrong halfway across open water, and no certainty on any single crossing that land actually existed where the currents and the stars seemed to suggest it should. Entire communities committed themselves to journeys that could just as easily have ended in nothing but open water and silence. Generation after generation, expanding across a section of the planet larger than any empire before or since. That is not a perfect parallel to interstellar flight, and it would be dishonest to pretend the distances are remotely comparable. What it does share, exactly, is the underlying shape of the decision. A species choosing to commit real people, real risk, and real multi-generational effort to reaching somewhere it could not yet see clearly, guided by nothing more certain than pattern, patience, and the accumulated skill of everyone who had tried something similar before. There is a reasonable, evidence-backed case that this specific impulse is not incidental to being human at all, but sits somewhere close to the actual point of it, biologically and culturally both. Populations that stayed rooted, generation after generation, in one single comfortable valley, did not go on to fill an entire planet. Populations willing to risk everything on the strength of a star pattern and a hunch about ocean currents did, eventually, reach nearly every habitable coastline on Earth, centuries before anyone had a word for navigation as a science. Proxima Centauri is only the next hill on a very long, very old list of horizons. This particular species has never quite managed to leave alone, and if you have ever stood somewhere unfamiliar and felt the pull to see what was over the next ridge, that same old impulse is what tonight's entire episode has actually been about. Traditional wayfinders trained for years, sometimes decades, before ever captaining a real voyage, apprenticing under navigators who had themselves apprenticed under someone else entirely, a chain of transmitted expertise not so different from the multi-generational discipline a real starship crew would eventually need to maintain. Modern navigators studying those same techniques today still find details nobody has fully reconstructed. An entire body of accumulated, informal expertise that took centuries to build and very nearly vanished within a single generation once easier instruments made it feel unnecessary. Everything this episode has walked through, the bombs, the fusion pellets, the paperclip weight chip riding a beam of light, the trapped particle that would erase a ship if it ever touched the wall meant to hold it, the centuries of gaskets wearing down in parallel, the cathedral, nobody who laid its first stone ever saw finished, comes down, in the end, to a single reframe worth holding onto after everything else fades. Ships don't actually cross distance, they trade for it, in time, in trust, in the willingness of people who will never personally see the far end of the journey to build it anyway, one careful decade at a time. That trade is not a metaphor dressed up to sound poetic. It is, quite literally, the accounting every design this episode has walked through has been running underneath its numbers, whether the engineers who drew each one up ever phrased it that plainly to themselves or not. So, after everything, how hard is it, really, to reach Proxima Centauri? Hard enough that chemical rockets, the only propulsion humanity has ever actually flown, fall short by a factor of thousands. Hard enough that the fastest realistic engine anyone has seriously designed still measures the crossing in decades at its very best and millennia at its ordinary worst. Hard enough that the one technology fast enough to arrive within a single human generation can only carry the mass of a paperclip and nothing larger, nothing alive. Hard enough that the one fuel dense enough to solve the entire energy problem can never once be allowed to touch the container built to hold it, not for a single second across 30 full years, and hard enough that the most elegant fix of all, bending space itself rather than crossing it, still depends on a substance nobody has ever actually held in their hand. That is how hard it is, genuinely and precisely and unglamorously hard. In 10 distinct ways, this episode has now named one at a time. None of them fictional, none of them solved. And yet, Proxima Centauri was never far away. It was only ever far away in patience. And patience, unlike distance, is not fixed. It is not written into the geometry of space the way 4 light years is. It is something every generation gets to spend a little more of, if it chooses to, adding its own careful decade onto everything the generation before it already built and could not finish alone. Whether this particular civilization, fractured and distractible and magnificent in its own ordinary way, ever spends enough of that patience, sustained without interruption across the centuries a real mission would actually require, is a question this episode cannot answer either. And honestly, was never really built to. It can only note, quietly, before the night closes, that the light is still arriving, patient and steady and 4 years old, exactly as it has for as long as anyone has been alive to look up and notice it there. You can still see the nearest star to our sun with nothing but your own eyes, close enough to touch, precisely as it looked at the very beginning of tonight, before any of this was explained. That has not changed, and tonight, it is not really supposed to. Tonight, we've drifted through bombs turned into engines, sails thinner than a soap bubble, a trap holding the most dangerous fuel physics allows, and a bubble of bent space built from matter nobody has ever touched. Together, we've wandered from a single point of light in a dark sky all the way down to a gasket wearing thin somewhere inside an imagined ship, and back out again, past a star that might be erasing its own planet, past cathedral builders who never saw their spire finished, and settled, finally, on patience as the only real currency any of it was ever spending. None of that distance was ever really out there, separate from you. The star, the sail, the centuries of engineers who will not live to see their own work finished, the 4 light years that refuse to shrink no matter how carefully they are measured. All of it is part of the same universe holding you right now, the one that grew the atoms in your body long before any of them knew what a star even was. You were never watching this from the outside. If your eyes feel heavy, let them close. That is not the episode failing to hold your attention. That is the entire point of it, finally arriving. If this felt like home, leave a comment when you wake up, and let this quiet corner of the universe know you were here for it, drifting off somewhere under the same slow, patient sky. The universe will still be here when you wake up. So will we. Good night.